Masters in Power Electronics and Drives from Mepcoslink Engineering College, Shivakasi. And Sir has did his full-time doctorate at NIT Tiruchirappalli in the area called Power Electronics Applications to Power System. And he is presently working as a assistant professor in Department of Electrical and Electronic Engineering, NIT Silchar. And before that, Sir worked as an associate professor in Energy and Power Electronics Department in School of Electrical Engineering, VIT. And Sir has published more than 50 papers in referred international journals and also the conferences. And Sir is also a reviewer in some major journals like IEEE, IET, elsewhere, Taylor and Francis, Springer, and also a lot of other journals. And Sir is also serving as an editorial board member for few of the journals. He has given number of lectures and also the hands-on training programs based upon the power electronic concepts, power system concepts, and also drives, fax controllers, smart grids, etc. And Sir is also a member in board of studies in various institutions. He is also guiding a number of BTech, MTech, and also the PhD scholars. His areas of interest are power electronics, power system, renewable energy sources, power electronic drives, smart grid technologies, optimization techniques, fax, and also HVDC converters. So I feel a great privilege to introduce Dr. Sreejith, sir. Thank you, sir. Thank you. Sir, now you can start your session, sir.
Thank you very much. Now the slide is visible, right, sir?
Yeah, yes, sir. Yes, sir.
Okay. So very good afternoon to all. And first of all, let me thank the coordinator for inviting me for this program. And let me thank the faculty who gave introduction about me. Anyway, sorry because some network issues will be there because I'm in car on the way from Shillong. So there may be some network issues in between. So let it be. We'll try to make best out of it. So for the next 1.5 hours, let me deal with the topic solar PV and grid integration. Okay, so these are the presentation highlights. We'll start with conventional energy systems. Okay, but because what we are going to see is a solar, that is a renewable energy source. So before going into renewable energy source, we'll see what is a non-renewable energy source, why we are going to non-renewable energy sources. I mean, what are the issues with non-renewable? So like this, we'll see, and finally we'll end up with renewable energy systems. Okay, then we'll see what are the types of renewable energy systems, because what we are going to see is solar, but apart from that, there are a lot of renewable energy systems. So those things we'll see in detail. Then we will move on to the various components in solar PV systems. So the basics of what are things, why the efficiency of solar panel is very less, what is a tilt angle, all those basics we will see in this one. Then we'll see the grid integration. Okay, because whatever solar we are solar power we are generating, most of the things are going to grid. So what are the issues we have when you're connecting to the grid, and what are the types of solar systems are there? I mean, what are the types of inverter? All such things we'll see in grid integration. So I have planned to complete the entire topic, these things within 1.5 hours. And once the session is over, if you have any queries, you feel free to ask. Okay. Now let me start with non-renewable energy sources. Okay. So from the name itself, it's clear that they are not renewable sources. They are not renewable in nature. Okay. So even though they are natural resources, even though they are, once again, let me take the pointer. So even though they are no renewable, I mean, they are naturally available sources. Okay. But they are not renewable. That means we cannot remake it, or it cannot be replenished. So once you are consuming that, nothing will be left off. That's why they are called as non-renewable energy sources. Okay, and if you take non-renewable energy sources, so most of them will be coming under fossil fuels. Okay, fossil fuels. So fossil fuel, in the sense, they have been formed from the fossilized remaining of plants and animals. And if you take fossil fuel, three things are there. One is a coal, other one is oil, and the third one is gas. So these three are called as fossil fuels. Okay, and they have been formed as the fossilized remainings of plants and animals. If you see the worldwide, okay, if you take electric power, 66% of the power generation is from fossil fuel. Okay, I mean, if you take only electric power, and around 95% of the world's energy is from fossil fuel only. Okay, so 66% is from fossil fuel. That means electric power. And if you take the whole then 95% of the energy is generated from the fossil fuel only. Okay. For example, let's take our day-to-day life. Okay. So if I'm taking what is that, electric, if you're taking what is that, electric power, so most around 69% of power generation in our country is from thermal power plant. So most of the power, it is coming from a fossil fuel. Okay. If you go to a kitchen, you may have a natural gas cylinders, so that is also a fossil fuel. If you are driving your vehicle, as of now, when you go for a conventional vehicle, they'll be running in petrol or diesel or gas. They are also fossil fuel. So in a day-to-day life, everything is running with fossil fuel most of the times. Okay. And one thing is that there is a there you can think that around 95% of the energy, okay, requirement is satisfied by fossil fuel. Then we need to be happy for that, because, right? Because if there is some source which can satisfy 95% of our requirement, okay. But then why we need to go for the next, renewable energy sources? Because one side I have a source which can satisfy 95% of the energy requirement. Okay, so if such things are available, then why we need to find the alternate source? That's a big thing. Okay. Now let's see what is the issue with the fossil fuel. Okay, what are the issues with fossil fuel? First thing is that they are not renewable energy sources. Okay, if you consume it one fine day, it will get over. After that, nothing will be left. Okay, that is the thing. If you see graphically, okay, if you see this graph, okay, so there we have seen coal, gas and oil. If you see the green color coal, the entire coal war will get over by 2100 as per this graph. See, in a country where 69% of the power generation is from thermal power plant, so you just see one fine day, if the entire coal is getting over, then where will go for the power generation? That's the thing. Okay. And another thing, if I see on gas, okay, leave gas. If you go for oil, by 2051 or by 2058 or something, around that, the entire coal will, oil will get over. See how many vehicles are running on the road with, oil, because either you'll go for petrol or diesel for gas, but most of the times you'll go with petrol and diesel only. Okay, so that also will get over by 2058. So as per this graph, if you are using the fossil fuel, or if you are depleting the fossil fuel in this manner, nothing will be left of after 50 to 60 years. Okay, see, 95% of the energy is from fossil fuel, but those things will get over within a short period of time. Okay, so after that, what is next? That's a big question, right? So some alternate fuel has to be there for this one, and that should be renewable in nature. That is very important. See, some alternate fuel, if you found, then it's not, it's different. We need to find an alternate for this one which is renewable in nature. That means it should be available always. It should not end. Okay, so that is the thing. This is about the availability of fossil fuel. Okay. Now let me go to the, okay, if they are available, if these fossil fuels are available, let's see what are their effects. Okay, assume that such kinds of fossil fuels are available in a large scale. Okay, but there are a lot of effect with fossil fuel. You see, okay. The first one is the main drawback of fossil fuel is pollution. Okay, that's important, because that's an important thing when you go for fossil fuel, pollution, right? If I take a thermal power plant, you can see how much it's polluting the atmosphere. Just see how much pollution is coming from a thermal power plant. Or if I see the vehicle which is running on petrol or diesel, how much it's polluting the atmosphere. So one of the important issue when you go for a fossil fuel is the pollution. Okay, it is a lot of emissions will be there. Okay, so along with the emission, when you go for emission, this fuel, these gases are emitted, it will be affecting the health of people. That is one thing. Apart from that health issue, there are a lot of other effects with these emission. One is called as global warming. I think you can hear, you can see it, right? Global warming. There are a lot of dioxide in the atmosphere, and we are in the fourth position with emission. Okay, in case of emission, India is in the fourth position in the world. Okay, so what happens is that when the radiations from the sun, okay, comes to the earth, a part of the radiation will be absorbed by the earth, a part of the radiation will penetrate into the earth, and some portion of the radiation will be reflected back by the earth. This is what happens normally. Okay, since the earth is absorbing some radiations, it will be warm. Okay, that means the temperature of the earth will be, it will be a more medium one. Okay, such that we are able to live. If the earth is not absorbing any radiation, then it will be very cool. It will be in some -°C, and we won't be able to live. Since it is absorbing some radiation, the temperature is different, so that we are able to live. Else it will be like other planets. Okay. So some portion of the radiation is reflected back by the earth. It has to go to atmosphere. But what exactly happening is that because of these fossil fuels, since the emission is there, all these gases will get accumulated in the surface or in the surface of the atmosphere. And whatever gases they are reflected, whatever the radiations which are reflected back by the earth, they are reflected back to the earth again by these gases. They can't penetrate and go. They'll be reflected back. So again, these radiations will come to the earth and it will increase the temperature of the earth. We'll generally call it as global warming. So burning of fossil fuel is one of the very important cause for global warming. Okay. Then it's not only ending like this. Okay. As the gases are getting accumulated in the atmosphere, when it rains, okay, they'll get diluted with the water. They'll get mixed with the water, and they'll come to earth as acid rain. Okay. In India, we don't have that much, but in other countries, the effect is there. That will kill the organisms which are there in the earth. Okay. We are largely dependent on those organisms too. So pollution availability is an issue. First one, pollution is there, greenhouse emission, global warming is there, acid rain is also there. So these are some of the effects of fossil fuel. So first one is the availability. So we need to find an alternate source which is renewable. Second one, these effects. So what are alternate fuels which you're going to consider should not pollute the atmosphere. There should not be any global warming from that, or there should not be any emission or acid rain from the new alternate source. That's what we want. Okay. So now let's see what is a renewable energy source. As the name indicates, it's a renewable energy source. Okay. That means if non-renewable energy sources cannot be remade, then obviously it's understood that the renewable energy sources are available always. They are renewable in nature. For example, if I'm taking solar power, okay, today sunlight is there, tomorrow also sunlight will be there, maybe cloudy, rain, that is different, but sunlight will be there, and day after tomorrow also it's available. We can't find a day where there is no sun at all, right? We can't tell that sun will never rise, right? Then that's all done. So like this, when you go for a renewable energy sources, it can be replenished again and again by nature. It will come automatically. Okay, so they are called as renewable energy sources. Okay. And if we take our renewable energy sources, there are a lot of renewable energy sources. We have solar, you have wind, we have biomass, hydro, a lot of renewable energy sources are there. Okay, but obviously, if you see all such things, we'll be mostly dealing with solar and wind, because as far as our country is concerned, we are mostly concentrating on solar and wind. If you see worldwide also, even though a lot of renewable energy sources are there, the focus is mostly on solar and wind. Here, just I have categorized into two. It's not with respect to renewable and non-renewable energy sources. Solar is separate and a lot of other sources are separate. You can see here coal is there. There's a non-renewable, oil, non-renewable, gas, non-renewable, nuclear will go on that side. Hydro, wind and all renewable energy sources. But they are categorized into a single one. Okay, that means they are coming under some specific thing. Whereas solar is separate. So this actually shows what is the difference between, okay, those sources and solar sources. Okay, just example, let me tell you what is the difference between these energy sources and the solar power. If I'm taking coal, okay, that means a thermal power plant. What exactly we'll be doing is that the coal is crushed, okay, it is ignited, okay, then it will be boiling the water, it is converted into steam. That steam will run a turbine, that turbine will generate generator, then electric energy will be there. Right? That means from the input of coal and the output what we get is electrical energy. In between that, you are having lots of, stages. Most of them are mechanical stages too. Okay, so there will be lots and lots of power loss in between the stage, and the efficiency will be very, very less in the end. Okay, okay, let this be non-renewable. Okay, if you say nuclear, also the same thing is going to happen. Only thing is that as far as the thermal is concerned, we'll be burning coal and we'll be getting all this output. Whereas when you go for a nuclear power plant, it just by nuclear fission or something will be generating heat that is used to boil the water. So that also working at the same principle after this. Okay. Okay, they are non-renewable energy sources. Okay, when you go for renewable energy source like wind, exactly the same thing is happening there also. Wind will enter into the blade, wind will rotate the blades, okay, which is there in the nozzle. Okay, then this blade will be connected to a low speed shaft. Okay, then in order to match the speed, we'll be having a gear mechanism. That gear mechanism will be converting the speed and it is connected to a high speed shaft. Then it is running, it is actually driving a generator. So from the wind to the electrical energy, still you have a lot of stages in between. Okay, so a lot of power loss will be there. Okay, so that means whatever sources which are say there in the left side, they are having a lot of stages in between the input and the output. To the solar power. Okay, so when sunlight is falling on the solar panel, it will be directly converted into electrical energy, right? There is no intermediate conversion in between solar power, output is electrical energy. So this is the one source where the input solar is directly converted into electric power without any intermediate stages. But after this, you'll be using some kind of conversion technique with power converters, okay, just to make the voltage stable and all. But that is not an issue because most of the converters which have efficiency more than 95%, so I don't want to worry about those things. But this is the only source where we have direct conversion from the source to the electric power. That's why this is separate. It is kept separate in this slide. And if you see the basics of photovoltaic cell, okay, so when solar radiation is falling on the PV cell, okay, what will happen is that same as the radiation which is falling on the earth, three things will take place. One is that, okay, the few part of the radiations will penetrate through the solar cell and it will go off. That will be converted into heat. Another part of the radiation is absorbed by the solar cell, and the third one is some portion of the radiation is reflected back by the solar cell. So three things will happen. Okay, a part of the radiation will be reflected, a part of the radiation will be absorbed, and a part of the radiation will go penetrated into the solar panel. Okay, so out of these three, only the radiations which are absorbed by the solar panel will be converted into electric power. If you take solar spectrum, okay, if you take solar energy from the sun, when it comes to the atmosphere itself, lot of power will be lost, right? Then after, lot of energy will be lost, radiation will be lost. Then after coming from the atmosphere, when it is reaching earth also, lot of radiations will go because it will get diffused, okay, lot of things will happen. Again, when they are entering into the solar panel, a part of the radiations will go off, right? It will get reflected. A part of the radiations will penetrate. Only the portion of the radiation which are absorbed by the solar panel will be converted into electric power. Okay, so that is the thing. Okay, so not all the radiations which are falling on a solar panel will be converted into electric power. Only the portion of the radiation which are absorbed by the solar panel will be converted into electric power. That's it. Yeah. Absurd. Okay, so let me come to the next point. Okay, if you see the spectrum, that if you see the solar spectrum, you have a lot of waves. Okay, if you arrange with respect to the frequency, or if you arrange with respect to the wavelength, sorry, not the frequency, if you are arranging all these radiation with respect to the wavelength, okay, if you start from the shorter wavelength in the x-axis and ending with longer wavelength, then you'll be having shorter wavelength waves, like gamma rays, X-rays, ultraviolet will be there, then visible rays will be there, then infrared will be there, then the microwave, radio waves, all such things will be coming. Okay, so x-axis will be a wavelength, so it starts from the minimum wavelength to maximum wavelength. So when you take a minimum wavelength radiation, it starts from gamma rays, then ultraviolet rays will be there, then X-rays, then visible rays, infrared, all these things will be there. That means the solar spectrum doesn't have a radiation with, all the radiations won't have the same wavelength. Most of the radiations, they will be of different wavelengths as per the solar spectrum. Okay, now what is exactly happening is that, okay, let me tell you. Okay, 1 second. Okay, so according to Planck's law, okay, so what Planck's law tells that is that, yeah, the energy of the incident, okay, that means the energy is inversely proportional to wavelength. Clear? The energy of the incident photon is inversely proportional to wavelength. That means that the shorter wavelength radiations will have more energy, and the longer wavelength radiations will be having less energy. That is the thing. Okay, the radiations which are having less wavelength, they have more energy, whereas the radiations which are having more wavelength or a higher wavelength will be having only less energy. That is what Planck's rules tell. Okay, so the thing is that if you take shorter wavelength, the ultraviolet rays, then these gamma rays, is part of visible rays, all such things will be there. So they'll be having more energy. Whereas when you see the right side of the spectrum, longer wavelength, which will be infrared, microwave radiation, all such things will be having higher wavelength, but their energy will be very, very less. Okay, so now we can see within the entire spectrum, there are certain radiations which are having more energy, and there are some radiations which are having less energy. So it's clear now. Okay, So it means that you don't want to have a lot of sunlight into the panel. You need to have light with some specific wavelength. Then it's better. Rather than having, if you assume that lot of radiations are falling on your solar panel so that it will be, you will be getting more power. That is not the thing. Whatever falls on the earth, if it falls under certain wavelength, then only you will get the output. That is the thing. Okay. Now, okay, this is clear. That means energy is inversely proportional to wavelength. Okay, right. Now, as per the calculation, because there are a lot of calculations, so as per this one, Planck has calculated that the minimum wavelength needed is 1110 nanometer. So that nanometer wavelength radiation is having the energy to eject the electrons. Okay, so that is the spectrum. Let me come to the graph, then I'll tell you here. Okay. So as per the Planck's rule, okay, it stated that 1110 wavelength, nanometer wavelength is a one which has a minimum energy to eject an electron. So if we see 1110, it will be coming, actually 1 second, this is 1000, this is 1100, it will be around 1110 will come here. Okay, 1110 will come here. Okay, so if I see this side of the spectrum, 1200, 1400 and all. As per Planck's rule, the wavelength is inversely, energy is inversely proportional to wavelength, right? But you can see the right side, the wavelength is increasing, but it's understood that then the energy will be very less. So this is the minimum wavelength we need. So this side is not useful. Okay, this side is not useful. So that side also gone now. That side gone now. So now you can see a part of the radiation already gone. So you need to understand that it doesn't mean that all the radiation from the sun will come to earth. Okay, this part of the radiations will be going up. After coming to atmosphere, still a lot of things will take place, and there only a part of the radiation will fall on your solar panel. Now we can see the spectrum. A few of the things, few of the radiations, few wavelengths have been going off. Now we have only one portion here. You have only one portion here. Okay, and if you see here, okay, so this is 1100. So it's understood that 1000. Their wavelength is very less, so the energy content is more 800. All such things will have more energy content. But if you see this side, this ultraviolet rays, okay, they are having very low wavelength, so energy content will be very, very high. But because of the ozone layer, most of the ultraviolet radiations will never come to Earth. Okay, so ideally, I'm telling there is no ultraviolet radiation also. So forget about ultraviolet radiation too. So only this portion, only this much, okay, this much spectrum is converted into electric power. Even though the radiation is starting from minimum of 200 to 2200, only a part of the radiation is converted into electric power. So if we see the number of, the amount of radiation which is falling on a solar panel and the amount of radiation which is converted into electric power, it is very, very less. So if you see the input falling on the solar panel and the output electric power will get, the efficiency is very, very less in this case. Okay, that means compared to a portion of the compared to the amount of radiation which is falling on a panel, the output which you will be getting is very less because only a part of the radiation is converted. So it's considered that the efficiency of your solar panel is very, very less. This is specifically for a silicon based solar cell, but nowadays a lot of research is going on in the material of solar cell. A lot of people came up with lots and lots of new methods, a lot of new coatings, nanomaterials are there, then increasing the number of junctions in the diode. So all such things, the research is going on such that the efficiency of a solar cell will be increased. But when you go for a normal silicon based solar cell, theoretically the efficiency will be always less than 20. Okay, this is one of the reasons. Right. Apart from this one, after this, lot of losses will be there. Then partial shading will be there because certain times there will be a lot of shading in your solar panel. A lot of things will take place which will reduce the efficiency of your solar panel. Okay. Now let's move on to the next one. The position of the solar panel. Now it's clear that you have a solar panel. When light is falling on the solar panel, it will be converted into electric power, and not all the radiations are converted into electric power. Only a part of the radiation is converted into electric power. Now let's go on to the next one, the position of the solar panel. If you see the solar panel, okay, never you can see the solar panel kept it in horizontal position. Most of the times it will be inclined, it will be in some angle, it will be tilted in some angle. Okay, never you can see a solar panel in horizontal position. Okay, so there is a specific reason for this one. Let me tell you why it is not horizontal. Okay, so if I take this as our earth, okay, 1 second. Actually, now the drawing is a bit tough. 1 second. Okay, so if you see the Earth, in the Earth you have two hemispheres. One is called as northern hemisphere, other one is a southern hemisphere. Okay, and if you see the sunlight which is falling on the Earth, okay, so in the Earth in the middle we have the equator. Okay, so in the equator the sunlight will directly fall. Whereas when you go for the northern hemisphere and in southern hemisphere, the sunlight will never fall directly, it will be fall with an angle. Okay, so the sunlight will directly fall on the equator, whereas in northern and southern hemisphere, it will be falling on some angle. So as far as equator is concerned, since it's falling directly, you can keep the solar panel in horizontal position. Whereas if you go for southern and northern hemisphere, okay, since it is not falling directly, it is falling in some angle. If you keep the solar panel horizontally, only a part of the radiation will fall on your solar panel and you will never get a maximum output. So in order to make most of the sunlight falling on a panel, you will be tilting the panel towards the sun. Okay, you'll be tilting the panel towards the sun. So in case of southern hemisphere, you will tilt towards north, and in case of a northern hemisphere, you will tilt towards south. So that's why the solar panels are tilted. Okay, because the sunlight will directly fall on equator, the places which are near to equator. When you go for northern and southern hemisphere, it will be falling at some angle, not exactly directly. So if you keep horizontally on the Earth, only a part of the radiation will fall on that. So in order to make the panel facing the sun directly, we will be tilting it with some angle. So when you are going in northern hemisphere, you will tilt towards south. Okay, because if in the northern hemisphere, again if you tilt towards north, means nothing will come. Okay, so it is tilted to south. In southern hemisphere, it is tilted towards north. As far as our country is concerned, we are in northern hemisphere. So whatever solar panel we have in our country, it should always. Okay, so that is why solar panels are tilted. It should be facing the sun. Okay, but for laboratory purpose, we are seeing, right, people are putting horizontal. It can give output, but you won't get the maximum output from the solar panel in this case. And okay, now it's clear that it has to be tilted, right? But in which angle it has to be tilted? That is also important. I can't put 90 degree, or I can put 170 degree, 60 degree. Simply, I can't put the tilt angle like this. Okay. So there is some specific value for the tilt angle. Okay, so that is the thing. 1 second. So there is some specific value for the tilt angle. Let me show you what is the value for the tilt angle. Okay, so here you can see the angle at which it is tilted is called as a tilt angle. All these terminologies will be coming when you are calculating the power generated by the solar panel. Okay, because this tilt angle is very important. Okay, this is a tilt angle in our this is with respect to the country. In our country we are making this tilt angle. Okay, so if you see the zone 4, okay, because this is with respect to south. Okay, if you see the zone 4, you can see the 12 to 15 degrees is the tilt angle. Okay, so that's the thing, because if you see the latitude, okay, if you see the latitude of southern part of the country, it is from 12 to 18 only. So the same angle only we will be making as a tilt angle. If your latitude is 18 degree, means you need to tilt by 18. If your latitude is 13 degree, means you need to tilt by 13. So you can see the solar panels which are there in the southern part of our country, they'll be tilted by 12 to 18 degrees. Whereas just to see the top exactly in the north, you can see it is 30 to 36 degrees, because the latitude is different there. So there the tilt angle is also different. Okay, so presently I'm here in near the Shillong. You can see it's around near West Bengal and all. If you see, Yeah, it's around 18 to 24 degrees. Okay, here what we have, it will be tilted from 18 to 24 degrees. So the thing is that even though in the same country, the solar panel tilt angles are different. If I take a solar panel and keep it in the Silchar, the tilt angle is different. The same solar panel, same rating, everything. If I put it in southern, I mean, for example, if I put it in Bangalore, the tilt angle is different. Okay, so this is how the tilt angle is varying. It varies with respect to the latitude of that place. And this is another one important concept which you need to know. Okay, the thing is that even another declination angle, something called as declination angle, is also there when you go for a solar panel. So as we know, right, sun will start in one direction and it will end in another direction. Sun is rising in one direction and it will setting in another direction. That's what we have seen, right? But the thing is that even though the source and destination are the same, the path it is following will be different. Okay, that means the angle at which it is moving is different for each hour and each day. Each hour it will be different, each day it will be different, each season it will be different. Okay, so for example, you can see in this diagram it is given as June 21. It is from its east and west, it's given. Okay, but when the same sun, when it is in December 21, you can see the angle at which it is moving is different. Okay, even though the source and destination are the same, the angle in which it is moving is different. So declination angle plays another important role when you go for the calculation of solar power. Okay, so we can see location will change the angle, which will call it a tilt angle. Then each and every day, season, all these things, the angle will be changing. Okay, so with respect to season also, the solar panel has to be, position has to be changed. Okay, it's like this. Okay, you can see in winter, you can see the solar panel is tilted like this. In summer it is tilted like this, and in fall or spring it is tilted like this. So each and every season also, the angle in which the sun rays are falling on the panel will change. So these lot of parameters are there which will decide the solar panel. When you are going deep into the calculation of the solar panel, solar power, you can see that lot of parameters will be coming. You will be having declination angle, you'll be having hour of the day, then you'll be having a tilt angle. All those things will play a very major role when you go for the calculation of power generated by a solar panel. These are some of the terminologies which are used in solar. You have irradiance, you have irradiation, solar constant is there. That means the amount of radiation which is falling on the solar, atmosphere is different, and the amount of radiation which is coming to the earth is different. So the amount of radiation which is falling on the atmosphere is called as solar constant, and approximately the value is 1360 watts per meter square. Those things are needed when you are doing the calculation. Okay, then air mass, declination angle, time of the day. So a lot of parameters are there, terminologies are there when you are going to deal with solar. Okay, so these are the basic things. Okay, now let me move on to the next one, solar cell connection. Okay, so if you see the solar cell, okay, single solar cell is there. Okay, so that can have a maximum of 0.5 volts like that. That's all 0.5 volt, or approximately that was the voltage of a single solar cell. Okay. Find an application with 0.5 volts. Okay, so in order to increase the voltage, you'll be connecting them in series, which is called as a solar module. Okay, so first one is a solar cell, which is having lowest voltage rating approximately 0.5 volt, and you can find application with 0.5 volt. It's very rare to get an application with this voltage. So if you want to increase the voltage rating, you'll be connecting them in series, which is called as a module. Okay, for example, if I'm connecting 72 panels in series, I'll get around 36 volt. If I have 60 panels in series, I'll get approximately 30 volt. Okay, so that is called as a module. And for some small applications, this is okay. For small applications, it's okay. But still, if I want to go for some high application, high voltage applications where I want 230 volt and all, again I'll be connecting modules in series, which is called as a panel. Okay, so solar cell which is connected in series is called as a module, and still if I want to increase the voltage rating, I'll be connecting them in series, still it's called as panel. And so since all these things are in series connection, now the voltage rating will be increased. So if I want to increase the current rating, I'll be connecting those panels in parallel, which is called as an array. So cell, module, panel and array. Cell, module, panel, all are series connection. Array is a parallel connection. So depending upon requirement, you can go for a module, you can go for a panel, or you can go for an array. All those things are there. Okay. And this is our one. Okay, you have a cell, then you have module, then you have panel, and at the end you have array. So this is actually the configuration of a solar cell. So okay, this is a graph which shows how we are adding an series and parallel. In the first graph, you can see that I have a solar. See, it's very difficult to find, or it's very rare to find the semiconductor devices with ideal characteristics. If I have two solar panels, okay, surely there will be surely a slight difference between the characteristics. You can't find two devices with ideal characteristics. If you see power electronics, also we can tell that we can find diode with ideal characteristics, right? Or if you have thyristors, if you have two thyristors, surely slight difference will be there in the characteristics. Okay, so but in this case, I am assuming all two solar panels they are ideal. Assuming that having a voltage of 0.6 volt and a current of 0.8 ampere. So let me come to the second graph. If I connect them in series, I'll get 1.2 volt, because series connection will add the voltage, so it will be 1.2 volt, but the current remains the same as 0.8 ampere. So that is done. Still, if I connecting them in parallel, you can see the third graph. If we connect them in parallel, so the current is increasing from 0.8 to 1.6. So assuming them as ideal one, it's getting doubled, whereas the voltage is remaining the same. Likewise, you can connect them in series and parallel, such that in the fourth graph you can see that the current is increasing to 1.6 and voltage has increased to 1.2. So you can connect them in series and parallel such that you can get the desired voltage and desired current rating. Maybe in practical case, slight difference will be there in the voltage and current, but this is for the ideal case, and this is how we'll be connecting solar panels either in series or in parallel. Okay. Okay, so this is one you can see this is short circuit. There is a small typo error here, and this is also open circuit. Okay. So when you take a solar panel, okay, when you take a solar panel, the thing is that it has a short circuit current and open circuit voltage. Okay, and there are two parameters which we know. That means solar radiation is falling, so light will be there and heat will be there. Okay, so but the thing is that when you see a solar panel, okay, if you see the rating of a solar panel, everything will be given only for a certain condition. That means what are, for example, if I'm going to buy a solar panel, they'll give all the details specified for a particular temperature and radiation. That means most of the times they'll tell that all these characteristics are applicable only for 25 degrees centigrade and 1000 watts per meter square irradiation. That's the thing. Okay. Now let me consider that I have a solar panel with, well, I'm giving a lot of different radiations. You can see 1000 watts per meter square is given, 800 is given, 400, 600, all such things are given. And you can see the current here. When the radiation is 1000 watts per meter square, it's going to 4.5, whereas when radiation is 200 watts per meter square, it's 1. So the current will change drastically when the radiation is changing. Okay, so that's the thing which you want to know. So radiation, if the radiation is changing, the current in the solar panel from the solar panel will change. Whereas you can see the voltage remains approximately constant. Okay. Now let me show the next graph. This is with respect to voltage and current. And the first graph, you have seen the irradiation was varying, but it's plotted for a temperature of 25 degrees centigrade. Now let's come to this graph. Here, this graph is plotted for a fixed radiation of 1000 watts per meter square, but the temperature is varying. The temperature is 10, 25, 40, 55, and 70. You can see at 10 degrees, the 10 degrees temperature, the output voltage is around 23, whereas when the temperature has increased to 70 degree, you can see the voltage has decreased to 17 or 17.5. That means change in temperature will affect your voltage. The current is approximately constant. So change in radiation is affecting the current and change in temperature is affecting the voltage. Okay. So when you take a solar panel, okay, the specification will be given only for a particular temperature and radiation. So if temperature is changing, all those values will change, and if radiation is changing, all those values will change. Okay. Now let me come to another important concept of a solar panel, which is called as a maximum power point. Okay, so this is the IV curve of a solar panel. So let me take this first point. Okay, if I see the first point here, okay, this point I'm taking, some current will be there and some voltage will be there. So let me take this point, this one. Okay, so on the point 1, you can see some current and some voltage is there. Current is maximum and voltage is bit minimum value. If you multiply, I'll get the power. Okay, so that is the power at the first point. Now let me consider another point, point 2. Okay, let me take this point 2. Okay, in this point 2 also you have current, it is reduced very slightly, but the voltage has increased. So if I multiply it, I'll still get a power which is more than the first case. Okay, so that means the power is increasing and the power is changing actually. So let me go for the third case here. Okay, let me go for the third case here. So in this case, you can see the voltage has gone to its maximum, near the maximum value, whereas the current has reduced. So if we multiply this one, we will get a power, right? This power may be greater than the first condition, but it may be less than the second condition. Okay, that means you can see in the entire graph, each and every operating point has different powers. It's not fixed. Okay. So there will be only one point in the graph where if you're multiplying the, since it is easy, voltage and current are multiplied, you will get the power. So only one point in the graph where if you multiply the voltage and current, you will get the maximum power. Here, this is approximately this point in this graph. Okay. So this point, the voltage and current, if you multiply, you will get the maximum power. So this point is called as maximum power point. Okay, the point at which you are getting the maximum power. And the current corresponding to that is called as IMP, and the voltage corresponding to that is called as VMP. That's why when you see the specification of a solar panel, they will give what is VOC, what is VMP, what is ISC, and what is IMP. All such things will be given for a solar panel. But the thing that you need to understand is that all these things are given only for a specific temperature and irradiation. Now, considering this, if for the same solar panel, if this irradiation is changing, surely this point will change because your graph will be changed, right? When the irradiation is changing, you can see the current will change. So obviously the curve will be like this. Okay, then your maximum power point will be somewhere here. Okay, so if again still the irradiation is changing, current will change and your graph may go somewhere else. Again the power point is changing. So this power point is not fixed. It is changing with respect to irradiation now. Again, if the irradiation is constant and the temperature is changing, again your voltage will change. Again this power point will change. So, but practically, so what I told is that I'm keeping irradiation and I'm changing the temperature. Second case, I'm keeping the temperature constant, I'm varying the irradiation. But practically, both irradiation and temperature will vary always, right? Because with respect to the time, radiation will vary and temperature will vary. That means the maximum power point will change for each and every time period. Okay, whenever the irradiation is slightly changing, maximum power point will change. When the temperature is slightly changing, the maximum power point will change. If you have a fixed radiation and temperature always, then I have only one maximum power point and I can operate the device on that. But you can see practically the temperature and irradiation is always varying. So your maximum point will keep varying always. So we need to track or we need to find where the maximum power point is. So that method is called as maximum power point tracking. The method by which you are tracking the maximum power from a solar panel is called as maximum power point tracking. If there is no variation in temperature and radiation, you will have only one point, then it's fixed. But since that radiation and temperature is varying with respect to time, you need to go for the tracking of maximum power. You have a lot of methods for tracking maximum power. You have a hill climbing, perturb and observe. Then you have a lot of other things. Okay, incremental conductance is there. Then a lot of optimization techniques are there. All such things are there for tracking the maximum power from a solar panel. Okay. This is gonna leave it. Okay. Now, so okay, as of now it's clear. When you go for a solar panel, okay, it'll be converted into electric power. Then you'll be using it. All such things are fine. It's a direct conversion. No need of intermediate stages and all. The next question will come: why we need power electronics? Okay. One second. Let me have a cup of water. Then I'll come back.
Sir, Sreejith sir.
Hello.
Sir,
Yeah,
sir,
am I
now
audible
it's
there?
audible, sir.
Yeah. Okay. So
Previously
why
you
we
have
need?
muted you, sir. Fine, fine, sir.
Yeah, I just had a cup of water. Okay.
Fine, fine.
Right. So now let's see if we take a solar panel. What I have seen is that it's directly converted into electric power. Everything is fine, right? Now we need to see. So and what we have seen for other energy sources that it needs intermediate stages. Okay, but this doesn't need any intermediate stage. That's what we have seen. But now we need to know why we need to integrate power electronics inside PV cell. If we take a PV cell, the core of the PV system is a PV cell. Okay, it's the core of the system. It takes 40 to 50% the cost of your PV system will be from PV panel only. Okay, but the thing is that okay, if you want to get if you want to use this technology in an efficient way, that means if you want to use the solar power in an efficient way, or if you interface, if you want to connect this to the grid, then surely we need to go for power converters. Okay, without power converters, we can't use this in an efficient way. Or if you want to connect it to the grid without power converter, it is not possible. I'll tell you a few applications where you are using power converters. We need, if you want to go for maximum power point tracking, we'll go for power converters. Okay. And if you want to use it for AC load, then we need power converters. If you want to synchronize with the grid, we need to have power converters. So whatever applications you have with solar, we need to incorporate power converters inside. Maximum power point tracking, power converters are used. Inverters, power converters. If you want to change the voltage level, again power converters. If you want to connect it to the grid, I need a grid tied inverter which has the ability to synchronize with the grid. There also I need power converters. So everywhere we need power converters. Okay, so without that, we can't connect it to the grid, or we can't use the solar power in an efficient way. Okay, that's the need. And thing is that okay, so let me tell you two more things. One is the blocking diode, which is this is the basic which is used in solar cell. The thing is that when if I have assume that I am using a solar cell to charge the battery. Okay, so whenever the solar power is there, the output of solar panel will be there, which charges the battery. Okay, but at night time when there is no solar output, okay, so the potential of the battery is much greater than the potential at the solar panel because solar panel is not working. So what will happen is that the current will try to flow from the battery back to the solar panel. Okay, because their potential is very less. Okay, so in order to avoid this one, you'll be putting a diode which is called as a blocking diode. This is a blocking diode. Okay, so the function of this one, as per the name implies, it's used to block the reverse flow of current. Because you can see the position of the blocking diode whenever the solar panel is working, it is forward biased so that the current will flow through the battery. When solar panel is off, you can see that the battery, because of this battery, this diode will be reverse biased because positive is connected to the cathode of the diode, so it will be reverse biased. So this will mean a diode will never allow the reverse current of flow, reverse current flow from the battery to your solar panel. That's why they are called as blocking diodes. Okay. Then, as long as the voltage produced by the panel is greater than that of the battery, charging will take place. And during night time or when there is a less output or there is no output from the solar panel, there's an option, there is a chance that the current will flow reverse. That means from the battery to the solar panel. In order to avoid that, we'll be going for a blocking diode. And another one is called as a bypass diode. Okay, so if you see bypass diode, okay, what will happen is that you have something called as a partial shading in go for it. This is taken from a reference paper IEEE. The thing is that you have something which is called as a partial shading. That means if I take, I'll just show you one picture. If it is there for a partial shading, you can see that this is a shading from the okay, some electric poles. You can see shading is there from the trees. These are animals standing above the solar panel. So a lot of shadings will be there, right? When you are connecting lot of panels in series and parallel, if shading is there in some panel, then the output of this panel will be different compared to other panel. Right? The output power will be, or output voltage or current, all such things will be different compared to other panels, and it will be creating a lot of issues in the panel. In order to avoid such kind of issues, we'll be using something called as bypass diodes. Okay, this is mostly because of partial shading condition. If there is no partial shading or if there is no dust and all, then it's okay. But because of all such things, there'll be some difference between the current or voltage which is in one panel. Okay. So the thing is that in order to avoid such kind of things, we'll be going for a bypass diode. So from the name, by the name itself, it implies bypass. It will bypass that panel. Okay, such that will never affect your circuit. 1 second. You can see here This is a shaded panel. Okay, so what will happen is that current will flow from this one panel, then it will enter to this bypass diode, and then now it will go to the other panel, right? So this shaded panel is bypassed because the output of this panel will be different. Okay, it makes a lot of current flow inside this one, then it will get heated. That will call it as hotspot. Okay, you can see here, this is actually a thermal image from a journal. You can see this is a panel. Okay, it's getting heated. Okay, here all such things are getting heated. This will form hotspot. Okay, in order to avoid these things, we'll be connecting a bypass diode. Okay, so this will bypass the panel such that the things are safe. Okay, and now another one is that, okay, now all things that their solar energy is very clean, which is green, all such thing will tell, right? But there are a lot of issues with solar. The first one is its intermittency. That means they are volatile in nature. We can't predict that when you will get more output or when you will get less output. What will happen next, that also we don't know, because the output of the solar panel depends on the irradiation, it depends upon the temperature, it depends upon the day, it depends upon the climate. All such things will change the output. So as far as solar is concerned, you will never get output with the normal solar cell. You are not getting output at night, so leave it. Only at daytime you will get. In the daytime also, it depends on irradiation, it depends on temperature, it depends on season. In each and every climate, the output is different. Okay, each hour of the day, the output is different. So everything will be changing your solar output. That's why it is intermittent in nature. This is a practice developed. You can see that from the morning 6 to evening 6, you can see the output power is going like a curve, right? So the output power is varying with respect to time. Okay, and the same thing, this is the same practical curve with respect to various seasons. For the same panel, each and every season is giving different outputs. Okay, so we can't connect this directly to the grid or to any load because everything is fluctuating, everything is varying with respect to time. So we need to stabilize this output. Okay, so for that, surely we need to go for power converters. Okay. So if you see the components of a solar, so hope it's understood that these are the few reasons why we need to go for power, because solar output is not fixed. It varies with respect to time. I can't connect it to a load which needs constant power. Okay, or see this fluctuation you should not directly inject to the grid. So it has to be stabilized and it has to be injected to the grid. So we need a power converter. We need to use power converter, if you want to eliminate all such issues in a solar panel. Okay, because we can't change the irradiation level and all which is coming directly from the sun. We can increase as per our wish, right? The only thing is that we can control the power by using some power converters so that we can inject to the grid. Okay, we see the components of the solar system. So as we know, solar array is the heart of the system. Then we'll be having a charge controller. So charge controller is needed if you are using a battery. Okay, because if you take a solar system, okay, at daytime you'll be getting output, and as of now at night time you don't have any output, right? So at the night time, if you want to get power, then we need to use this store it in a battery, and I need to use it at night time. So I need a battery backup. Okay, so as again, if you're having a battery, then you need to control the charging and discharging of the battery. So then we need to go for a charge control. So if you're using a battery, you need to go have a charge controller also. If you're not using any battery, then you don't want any charge controller. Okay. Then you'll be having DC isolator, because when you go for a large scale power plants, then a lot of safety things are there. So you'll be having an isolator. Then you'll be having a battery. When you're going for a the output of solar panel is not available at night time, so we'll be going for battery. Okay, then we'll be having inverter. That means the output from a solar panel will be DC. Okay, so if you have a DC load, you can directly connect it by using a power converter, which will change the output voltage level and all. But if you want to connect it to AC load, okay, it has to be converted into, it has to be inverted and it has to be given to the AC load. There we need an inverter. And if you want to connect it to grid also, if it is a grid tie inverter, again this inverter is needed. So if you want to use it for a lazy load, or if you want to use it for connected to the grid, then I need to go for an inverter. Then lot of other things, meter, fuse box, all such protection things are needed when you go for a system. So it doesn't mean that only solar panel is enough. Along with solar panel, all such components are needed when you want to go for a solar PV system. So this I'll leave it. This one I'm skipping. Okay, this is also I'll skip. Now let me tell you. So this is a basic solar system we can have. I can have a PV, I can have a charge controller and a battery. because during daytime what will happen is that current will enter, I mean PV will be output is there, it will be directly given to the load and part of the power will be saved to the battery. At night time what will happen is that the power which is stored in the battery will be given to the load. This is for a DC load. Okay, so this is a basic simplest solar panel you can have. I think this is one application which you might have seen in the newspapers, right? The same thing. She is selling corn. Actually, she want to cook the corn, so we need to blow air. Okay, so initially she was blowing with hand. Now by the use of solar panel, you can have see a solar panel here. I can have a battery backup here, and I think some fan is there. So it will be driving the fan. It's a DC load, so that she don't want to blow anything. So this is one basic application of a solar panel. Okay, but when you go for a bigger application, I can't use this one. I need to go for different configuration like this. Okay, so I need a solar panel. This is the heart of the system. Okay, then I can go for a DC to DC converter because the output is a fluctuating nature. So that depends upon the time, it depends upon the temperature, all such things. Okay, but if I want a fixed DC voltage in the output, if I want to go for a battery charger or any application which needs fixed DC voltage, means I need to convert this one to a fixed DC voltage. So if you want, it's a DC, right? So if you want to step up the DC, then I can go for a boost converter. If I want to step down it, I can go for a buck converter. Or else certain times I need to step up and sometimes I need to go for step down, means I can go for a buck boost converter. Anything can be used as per the requirement. But now we have a lot of other converters too, right? We have a theta converter. Then I can go for what is that? Loop converter, quadratic boost converter. All such converters are there when you go for this DC to DC converter. Okay, something called single-ended primary conductor. All such things are there. So we can use any DC to DC converter when you go for this power conversion. Okay, depends upon the application. Okay. Now the next thing is that if only DC load is there, this is enough. You can directly give to the DC load, or you can store it in a battery. And MPPT is also maximum power point tracking also used. But the thing is that if you want to connect it to a load which is AC, because you can see the 90% of the loads or 99% of the loads which you have at your home is working with the AC supply, right? We'll give always AC supply to them. Okay, only thing like small remotes and all will work with DC, will give directly DC. Others, even though they are working in DC, like a laptop or a mobile charger, all these things are working in DC only, but the supply which we are giving to them is AC. So we need to convert this into AC. So I need an inverter in this case. And if you want to connect to the grid, I need to go for an inverter. So these are the power converters we need when you want to use the solar power in an efficient way. So without solar power, nothing will be working. Sorry, without power converters, nothing will be working perfectly. You can see it. If these two things are not there, then nothing will work perfectly. Okay. And this is the diagram. Solar array is there. And if you have a battery, then you need a charge controller. Okay. And if you want to have an AC, I need an inverter. Okay. If you are not using a battery, I don't want a charge controller. A simple DC-DC conversion is enough. Charge controller is the one which is used to control the charging and discharging of a battery. That also it will be done. Okay. So when you go for a charge controller, we need to know why. Because charge controller, right? Solar insulation is an unreliable source of energy. We don't know when voltage will go down, when voltage will increase, when voltage will change. All such things we don't know. But as far as charging is concerned, it has to be fixed, right? And so such things will be going for a charge control. Okay. Preventing overcharging and deep charging battery is important. So we'll be going for a charge controller for such kind of things. If you don't have a battery, I don't want to go for a charge controller. Yeah, this is how it's used. Battery is there, solar panel is there, and we have a charge controller. This will control all such things inside our circuit. And this is a typical graph of a charge controller. You can go for any kind of things. The first one is its main job is to control the power charging and discharging of the battery. It has to safeguard the battery. So the first one is VR. Okay, it is actually voltage regulation or voltage regulating. The thing is that, so see, there is a limit, right? We can't go for the overcharging of a battery. So battery has to be charged up to certain limit only. That is given by this voltage regulation mode. So when the charge or voltage in the battery is up to this limit, it will be automatically cutting off the battery from the source. So that means if I give 5 volt, means when it reaches 5 volt charge, automatically that will get disconnected. Okay. Then voltage regulation hysteresis. Okay. So voltage regulation hysteresis means my battery is charged. Okay. I have connected to the load. So when it is connected to the load, battery will start discharging. So when it has to be connected back to the source again, that is decided by VR hysteresis. Okay. So that depends upon the user, whatever value he sets. When the output of your battery is reaching this value, then automatically it will be connected to the source for charging again. That is it. Okay. And this is a low voltage. 1 second. This is low voltage. Okay. Detector. LVD means low voltage detector, because the thing is that we can never discharge the battery up to 0% level, right? 0% is SOC we can't reach. Okay, so then it will be fully drained. That's it. So some charge has to be maintained in a battery, that is given by LVD. So you are charging the discharging the battery through some load, it will go, charge will go down. Okay, but up to certain limit only it can be discharged. So when the charge in the battery reaches LVD, it will be automatically disconnecting the load from the battery. And LVD hysteresis is another one limit where, so the battery is, load is disconnected from the battery. Okay, now I got some source through which the battery is charging. So when the load can be connected to the battery again, that is determined by LVDH. Okay, so all these things are user defined value. Depending upon a requirement, you can put any value for this. Okay, but within the specification of the battery. Okay, so this is a function of a charge controller. Mostly power, again the same thing, power electronic converters one. And can go for a shunt type charge controller is there, series type charge controller is there, and you can go for DC to DC type charge controller. That's what I've seen, right? DC buck boost, all such things, and MPPT charge controllers. That means in case of DC to DC converters, if you vary the duty cycle with respect to the maximum power point of the solar panel, then you can go for MPPT charge controllers. So any type of charge controllers can be used. If you don't have battery, then you don't have charge controller, only DC to DC converter. Okay. Yeah, this is actually a shunt type charge controller. This is a series type charge controller. These are the types. Okay. Now let's come to the next stage, inverter. So inverter is another important component when you go for a solar PV system. Okay, because if you want to connect it to the load, which is AC in nature, or if you want to connect it to the grid, then you need to go for inverters. Okay, so there are three main classification of inverter. One is called as a micro inverter, other one is a string inverter, and third one is a central inverter. Okay, it depends upon your application by which inverter you need to use. Okay, let me tell you what are the types of inverters also. So this is a micro inverter. So as far as micro inverter is concerned, the thing is that each and every panel has its own inverter inside. So their rating is very less. That's why they are called as micro inverters. Okay. So as far as micro inverter is concerned, you can see each and every string or each and every panel has its own inverter. Okay. So the advantage of this one is that if you want to increase the rating, I just add a solar panel, that's all, because it will come with an inverter automatically. Okay, if you want to suddenly increase the rating of the system, is I can add one more panel which has an inverter inside, so no issues in that. Okay, and if any one of the panel is not working, or if any one of the inverter is not working, the remaining all will get connected and you will get the output. Okay, and one more important thing is that, see, since each panel is connected with a separate inverter or along with the DC to DC converter and inverter, so each panel can operate in a maximum power point. Okay, each panel have its own maximum power point. Where panel is having its own inverter or along with these DC converter, each panel can be operated in a maximum power point. That, okay, so that is another advantage. Okay, so we can easily increase the rating. If one inverter is not working, also remaining will be connected, and a maximum power point is mostly utilized in this one. So you can track the maximum power point and you can operate in that region also. That is the advantage. Disadvantage, it's a bit costly because each one is having its own inverter. Okay, and another one, a lot of wirings and all are needed because each panel has an inverter, so connection is there. We need to connect them. I need to take to mains, and also a lot of wiring is needed when you go for a micro inverter. You can see here, yeah, this each panel is having an inverter. Okay, along with DC to DC converter, so everything will work on a MPPT. So that is the advantage. But the thing is that this is used for low voltage, low power applications. Okay, like from 200 to 300 watts. So whatever theory I told, clear? Because you can see, since it features one inverter per PV module, it has the best MPPT capability of all the configurations. That is one of the biggest advantage of a micro inverter. Okay. Right. So this is mostly used for small scale PV plants and mostly for domestic use. Okay, for small scale system, that's the rating we have seen, right? It's from 200 to 300 watts or something. So it's only for small scale plants. It's mostly utilized. Next one is called as a string inverter. A string inverter in the sense, a string of solar panels will be there. You'll have only one inverter for them. Here you can see 1, 2, 3, 4, 5 solar panels are there. You have only one inverter for the entire string. Okay, so this is actually the string inverter. Okay, so the advantage of this is you don't have much wirings for this one. Okay, and you can see here. One second. Yeah, here you have 5 solar panels and it is connected to a single inverter. So number of inverter is very less. Okay, the cost is also very less, clear, and less wiring needed and all. Okay, but the problem with this one is that you are having 5 panels and only one inverter in this. That means that this inverter can work only on one maximum power point. So it may be the maximum power point of any of the panels, or it won't be the maximum power point of any of the panels. Okay, because 5 panels are in this one, each one is having their own maximum power point, but inverter can work only even one maximum power point. That means the modulation index, it can be one value at a particular time, right? So then it can be the maximum power point of panel number 3, or all these panels will be out of its MPP also. So it depends upon the application. Okay, so that is another thing. And one more thing is that if I want to increase the rating of this one, if I am increasing one more panel as a 6th panel here, if the rating of the entire string is more than the rating of the inverter, then I need to increase the capacity of the inverter also. Okay, say for example, under the 5 panels are there, it's around 200 watts. Okay, and the inverter is 220 watt. If I add a 6th panel, then it will be 220 watt or something. Okay, or if I add one more panel, it is around 240 watt, but which is less than the actual rating of the inverter. Now again, if I want to increase the power rating, I need to increase the inverter rating also. So there is another issue with the string inverter. Okay, and single and multi string. So this is a string inverter. A number of PV cells are there, but you have only one inverter for each PV cell. I mean, for a number of PV cells. And you can see the application is from 2 to 20 kilowatts. So for medium power applications, it will be going for this string inverter. You can see here. I'll just tell you only the few things. Okay. And so this is with respect to the central inverter. You can see the thing is that here for 5 or 6 panels, it will operate only in one MPP value. Okay. And thing is that another one. Let me tell you, I just told the theory. Only thing is that it's mostly used for medium scale PV systems. Okay. So whereas when you go for that, the first one is micro, it's used for small scale. This is used for medium scale as rooftop and all. Okay. And the last one is a central inverter. Central inverter in the sense you have only one inverter for the entire system. You can see you can have n number of solar panels connected, but you'll be having only one inverter. Okay. So the advantage of this one is that you can have only one inverter. It's very easy to control, less cost, less wiring and all. But the disadvantage of this one is that if there is any issue in this inverter, the entire system will go off. That is the first one. And the second one is that see you have 100 panels connected, this inverter can work only in one MPP value. So the MPP technique is, I mean, that concept is not much utilized in this central inverter. Okay, central inverter means for how n number of PV cells you have, will be having only one inverter in that. Okay, so it's less costly. Okay, only one inverter is there, so it's not complex and all, its controlling will be easier. But only thing is that the inverter is going off, then the entire system will shut. And another thing is that we can't use it for the maximum power point because only one inverter is there for all these panels. Okay, and you can see here it's mostly used for large scale PV systems. It's mostly preferred in large scale PV systems. Okay. So this is actually central inverter. And nowadays, you know, right, because this is a never ending research. So a lot of people are working in this area now. A lot of works have been done in multi-level inverters also. There are multi-level inverters also. I mean, a lot of work is going on this one for the usage of multi-level inverters for the solar panel. Okay, And I think a few people are working in multi-level, they know the advantage of multi-level inverters. So as far as multi-level inverters are concerned, okay, so we can operate at less frequency and less harmonic discharges will be there. You can easily increase the power rating, you can increase the voltage rating, you can reduce the switching stress. So a lot of advantages are there with multi-level inverters. Okay. And the thing is that the output will be approximately a sine wave, so less harmonics. So, and when you go for a lot of industrial applications, nowadays multiple inverters are preferred. So the same type of inverters are used in solar PV systems now, okay? Because when you go for MLIs, you have a lot of configurations, okay? The thing is that you have cascaded H-bridge inverter, you have what is that, CMLI, I'll just show you the few things, okay? 1 second. You have a neutral point clamped inverter, you have flying capacitor converter, cascaded H-bridge converter, multi-level modular converter. A lot of type of inverters are there. Okay, it can be used for all renewable applications, but as of now, if you see the literatures, you can see NPC and CHP are mostly preferred in renewable energy systems. Okay, so this is another thing in which we can use for a solar PV system, multi-level inverters. Okay, so because see. One thing is that what we have done with power electronics is that we'll be using high switching frequency, right? Because high switching frequency is used because the thing is that water harmonics will be getting, they'll be of high frequency, so their magnitude will be less and it's very easy to filter them, okay? But the switching stress is very high, so all such issues are there. But when you go for MLI with the lower switching frequency itself, the harmonic content will be very less. So this can be used for PV applications too. Okay. And when you go for a solar panel, you can go for two kind of systems. One is called an off-grid system, or another one is an on-grid. Okay, off-grid or standalone. So off-grid means it's off the grid, no grid is there. A standalone means it's standing alone, it's nowhere connected to the grid. Okay, you can see here you have solar panel. Okay, it's connected to a charge controller, because when you go for an off-grid system, you will never connect it to a grid. Okay. So when you're at night time, you don't have any solar power. So usually you need a battery backup. Okay. So that's why you have a charge controller and you have a battery backup. Then an inverter is there. So depending upon the number of loads, it will be fed to the load. Okay. So this is actually an off grid. It's nowhere connected to the grid. Solar panel, charge controller, battery bank will be there. So daytime from solar panel will get power and night time from battery bank will be getting power. So this is the concept of off grid. Okay, and one more thing is that, see, this optional generator is optional, because see, we can't predict that always solar output will be there. There are certain times where we'll be having less output, some cloudy conditions will be there, or some rainy conditions will be there where we'll be getting less output from a solar panel. So at those conditions we can go for a diesel generator also, but it is optional. It doesn't mean that you need to go for a diesel generator, but that is optional, because so you can't predict when solar power will be going off. Okay, so that's why you need a optional generator. And next one is a on-grid system. As far as on-grid system is concerned, both it will be connected to the grid and it will be connected to the solar panel. So when you have output from the solar panel, you can connect it to the load. When there is no output from the solar panel, then you can get it from the grid. That's why it's a grid connected one. And there battery backup is not mostly used, because the thing is that as you are having both grid and solar, as long as you are having solar power, you won't be taking from the grid. If the output of solar power is less, or if you don't have any output from the solar power, you will be taking from the grid. So as far as on-grid is concerned, we'll never, most of the case, we'll never go for a battery. Okay, so this is on-grid system. But you can see here is that you can see this one, this is bi-directional. Okay, this is bi-direction, because there is an important concept when you go for a solar PV, which is called as a net metering concept, because it's one of the very important concept when you go for a solar PV system, that is called as net metering. I'll tell you what is net metering concept. Okay, so hope it's clear now. Okay, on grid system, I'll just show you one diagram with net metering. Okay, see, for example, okay, let me take a condition where I have a solar PV system, okay, which is connected to the grid and which is connected to the loads. Consider that my load is, for all the conditions I am taking 2 kilowatt as my load. Assuming that my load is 2 kilowatt. Okay. If the solar power is 1 kilowatt, means I can take 1 kilowatt from the grid. Okay. So it is 2. Now the second case, my output is, my requirement is 2 kilowatt and the solar power is generating 2 kilowatt, because it's exactly the demand. So I don't want to take anything from the grid. In the third condition, my load is 2 kilowatt and the solar power is 2.5 kilowatt. That means 0.5 kilowatt more than my requirement. In this condition, I can give the extra power back to the grid. That means 2 kilowatt I will be utilizing and the 0.5 kilowatt I will be giving it back to the grid. Okay. So what will happen is that at the end of the month, okay, how much I consumed and how much I given back to the grid, it is calculated and the net difference between them will be calculated and you need to pay only for the difference. Okay. For example, for an entire month, I have considered 100 units of power. Okay. But using net metering concept, I gave 80 units back. Okay. Then only you need to pay for the remaining 20 units. So that is called as net metering concept. Okay. Okay. So this is the case, right? If you have extra power, you can give back to the grid, and that concept is called as net metering. You'll be getting a lot of be having you need to pay only the difference. Okay, so that concept is called as net metering concept. Okay, that's one of the important concepts. Okay, and I'll just tell you one more thing. Grid tied solar system. Okay, so as far as grid tied solar system is concerned, it's an on-grid system which is connected to the grid. But the important thing is that the grid tied solar system and a normal solar system, the inverter used is totally different. Okay, if I'm using a normal inverter, it is different. If I use an inverter which is feeding power to the grid, then it is totally different. Those inverters are called as grid tied inverter because there is a lot of difference between a normal inverter and a grid tied inverter. For example, assume that I have an inverter in my home. That means I have UPS in my home, which has a AC to DC conversion. Then you have a battery. Then you have an inverter which is connecting to the loads. So the function of the inverter is to just feed the loads when the mains fail, right? Nowadays you have low voltage and a high voltage also. When your mains voltage is low also, that inverter will work. If the mains voltage is high also, that UPS will work. And if main fails also, that will work. That is usual. Okay. But whatever case it is, okay, the work of the inverter is just UPS is just to feed power to the load whenever there is an issue with the mains. So this inverter will be designed for some particular voltage and frequency, 230 volt 50 hertz. That's it. For example, if it is designed for 230 volt 50 hertz sine wave means it will work on that. It will never see what is there in the grid and all. Only when there is an issue with the grid, this will get connected to the grid. That is okay. But the concept of grid tied inverter is totally different. Okay, because when you go for in machines, you might have seen, right? If I want to connect two alternators in parallel or some transformers in parallel, I need to see a lot of conditions. The voltage should be the same, frequency should be the same, phase sequence should be the same, all these things should be the same as that. When you go for a grid tied inverter, okay, when you go for a grid tied inverter, the output is connected to the grid, right? So that means it has to it should be synchronized with the grid. So whatever voltage is there in the grid, the inverter output should match. Whatever frequency is there in the grid, the inverter output should be that the frequency. Okay. See, just considering a case where, okay, I have an inverter which is having so I'll take a normal inverter which is there with a UPS, okay, it's a 230 volt 50 hertz. That's it. If I use it for a grid tied case, okay, so assume that the grid voltage is 230 and the inverter voltage is 230. Okay, it's okay. Grid voltage frequency is 50. This output is 50. But the grid voltage will change with respect to time, right? You can see that sometimes it will be 220, sometimes it will be 200 and all. Assuming that the grid voltage is 210 now, but this is a normal inverter which I am using, the output of that inverter will be 230 volt. Okay, so one side you can see a grid which is 210, and another side you have an inverter which is having 230 volt. They are connected together. That means power will flow from the inverter to the grid back, right? Because potential is higher. So you need to synchronize with the grid. That means whenever the grid voltage is coming down, the inverter output will also should adjust according to that. Whenever the grid frequency is normally don't change, if slight change is there, the output frequency of the inverter should also change accordingly. That means the inverter should have the ability to synchronize with the grid. So that is actually a grid tied inverter, whereas in a normal inverter don't have the ability to work like that. Okay, so that is a importance of it. I mean, that is a property of a grid tied inverter. It will be synchronizing with the grid automatically. Okay. So this is actually the grid tied solar system. You can see this one. What will happen is that whenever there is a solar power, I mean, whatever solar power it is generating, if it is more than the demand, it will be automatically fed to the grid. Okay. And whenever there is no grid, the power will be given from the solar power to the load. But the thing here is that what happens if the solar fails? I mean, if what happens if the main fails and the inverter, solar output is more than the demand. See, for example, let me have a condition. You know, right? When you go for a solar panel, now when you go for a grid, there will be certain dates where we'll be going for maintenance, right? In some Saturdays, 9 to 5 power cut, or some issues there with the grid, right? What they'll switch off the supply and they'll they'll go for the maintenance. Consider that I have a grid-tied inverter which is supplying power to the grid and to the load. Now what happens is that this grid, they have shut down the grid. There is some issue or some maintenance in the grid, so they have shut down the grid and they are working on the transmission and distribution lines. Or let me have a grid-tied inverter on the other side. So here what is happening is that the power generated from the solar panel is more than the demand. Now the extra power has to go to the grid, but the grid is off. Okay. So what will happen if this extra power is going to the grid, back to the grid? Who are the people who are working on the grid, who are working on the transmission and distribution line? They will get affected because they are having the intention, they are having a thinking such that they are switched off the grid and no power is flowing in that, they are working. But if your inverter is feeding power back to the grid, means they will get affected. So this inverter, what it will do is that if the grid is failing, this automatically, it will automatically sense it and it will never inject power to the grid. So if grid is on, then only it will inject power to the grid. Excess power is there, it will inject to the grid only when the grid is on. If the grid is off, even though if you have extra power, it won't inject to the grid. It will automatically sense because it will synchronization is there. When the grid is off, your voltage and frequency reference will be 0, right? So automatically it will stop pumping power to the grid if the grid is failing. That is the property of this solar panel. Okay. And but even though there are, let me come to the last because at 3:30 I need to bind here. So even though there are a lot of advantages of advantage with the solar panel, there are few issues we have with the integration of solar panel into the grid. They are volatile in nature, right? Because for each and every timing, okay, the output is changing. If you're connecting such a source to the grid, right, it's very tough to go for dispatch because suddenly power will increase, suddenly power will decrease. For a specific load, normally we'll go for dispatch. How much a coal power means thermal can generate, all such things will be there. So believing that solar can give this much output, if you're going for a dispatch, if suddenly load is, if suddenly solar is failing, then I need to generate something extra on that side. It's very tough. Okay, so they are intermittent in nature, so it's very tough to incorporate them fully into the system. Okay, and second one is that we need to go for a lot of techniques, that we need to go for a lot of power converters when you go for solar PV. Even if we take wind also, if we take electric, fuel cell also, we need to go for a lot of power converters too. And one more, as we go for more number of power electronic devices, lot of harmonics will be injected into the system. That is another thing. Okay, so they are intermittent in nature. Okay, so injecting it in the grid will create a lot of issues with the grid. Okay, then as a lot of power converters are connected, lot of harmonic related issues will be there with the grid. So though a lot of issues are there, but still few things have been sorted out, and a lot of things are under research now. Okay, yeah, intermittent generation depend on season. See, for each season it will be different, for each day it will be different, the output is different, all such conditions are there. So it's very tough to integrate them fully into the grid. We can't tell that. See, what we have seen is 66% of the power generation is from fossil fuel. You can't replace all this by 100% of renewable, right? Because they're mostly volatile and intermittent. So 100% replacement is not possible as of now because of all such reasons. Okay. So a lot of problems are there. Okay. Power quality issues are there. Harmonic is there. All such things are there. Okay. That's all from my side. Actually, I was sort of for 1.5 hours. It's now 3:26. Okay. So if you have any queries, you may ask now. Let me open the forum for the attendees. If they have any queries, they may put it now. Let me try to answer. And one more thing, let me tell, because of time limits, if they are not able to ask the question in time, or if they're not able to get the reply, then just share the slide with my contact number, or WhatsApp number, and mail ID. If they still have any queries, if they're not able to ask now, they can freely contact in my WhatsApp, such that I'll help them out. Okay. If they have any queries, they may ask now.
Thank you, sir. And thanks a lot for delivering an excellent information and relevant information about the different types of fossil fuels, effects of fossil fuels, and also the basics of PV cell and also regarding the different angles which are mentioned in case of a solar panel, and also regarding different types of charge controllers, and also the micro inverter, string inverter, and also different applications of a solar panel. So these are the different information what you have provided regarding the today's topic has enhanced our knowledge a lot, sir. Thanks for the information provided by you. I, on behalf of St. Peter's Engineering College and also entire team, extend a very hearty vote of thanks to Dr. Sreejith, sir. Thank you, sir. Thank you very much for readily accepting our invitation and successfully completed today's session. Thank you, sir. Thank you very much.
Thanks, sir. Thank you
Okay,
very
sir.
much, and have a nice time. Thank you all.
Okay, sir. Yes, all the participants, today's session has been completed. So as Sir is busy with his schedule as he is going on a election duty to other states, so he has completed his session for today. So there will be as per the schedule, we will have a next session in the tomorrow's morning, that is at 10 a.m. So please be sharp in attending the schedule at the right point of time. So I am going to end the session for today. We will meet in the next session, that is tomorrow morning at 10 a.m. Fine, the schedule has been already kept in the WhatsApp group what is provided to you. Fine, thank you. Venkateshwara sir, hi.
Thank you, sir. How are you, sir?
Fine sir, fine sir. Bonara sir.
బాగానే ఉన్నాను సార్.
సార్ చూడండి బ్రహ్మయ్య సార్ గారు వచ్చారు.
మాకు ఎక్కడ ఉన్నారు, ఆయన వల్ల జాయిన్ అయ్యాను. Thank you very much, sir, for giving an opportunity to participate in our workshop. Thank you very much, sir.
Thank you, Venkateshwara, for joining.
Thank you, sir.
How are you?
Morning, మళ్ళీ కలుస్తాం.
Okay sir, sorry sir.
Okay.
Bye sir.